Hello everyone. Hello, my name is Vlad Chernov, and I'm the lead tutor for Compost. So I'm responsible for selecting tutors, and I'm responsible for writing a large chunk of the assignments. So you've probably seen my name on the mechanics assignment. So welcome. This is the first year 12 webinar, and today we're going to talk about mechanics. And I will start by describing Compost in a few words, so hopefully you get a better understanding, especially if you're new, to understand what Compost is and what uh, what we're trying to achieve. Yeah. So, okay. Well, first of all, uh, what is Compost? Well, Compost, we're trying to teach you to problem solve. Get the skills that you need to be successful at any university, and not only university, right? Because problem-solving skills are necessary for, well, to be successful at anything. Okay. We think of Compost this way. So if you want to become an athlete, you don't choose athletics A level and you don't go to athletics university. If you want to be an athlete, you start training hard, and you start training as early as possible. Okay, of course, to become an athlete, you might want to start when you're 4 or 6. With physics, I think the appropriate age to start is about 12 or 13. That's what. So we have Compost starts in year 10, and for that reason, you have to become a really good athlete. You have to train a lot, many hours a week. And the same to become a good physicist, or to become a great physicist, you need to study hard for many hours a week. That's my journey. So I started when I was 13. I started studying physics, perhaps 4 or 5 hours a week, maybe a little bit more at times. And yeah, I think that's what that's what made me good. I can't say I'm great or anything. I'm just good at physics. So yes, so Compost is a place where you can come after school and to study your favorite subject, which is obviously physics. And yeah, so great. 50% of our first cohort went to become students at Oxbridge. So which statistics we do not hope to keep up with, because we had 100 students at Compost. Now we have 1,000 students at Compost, and Oxbridge just doesn't have 500 places for our students. So of course, yeah. So that's what we are. We're not training you for Oxbridge. We're not training you for any particular exam. We just want you to become good at problem solving and physics, of course. So today we're going to talk about mechanics, but the structure of Compost. So there's a few things happening at the same time. So first, the Compost is the main Compost program. Compost program. And what does that entail? That means you have a small group in small groups of 8. Small groups of 8. You have tutorials every week. Tutorials every week. Then you have a homework, which is about 3 to 5 hours of homework every week. And this is mandatory. Yes, mandatory. And the tutorials every week are also mandatory. So we believe that to become good, you need to train hard, and that's what we are offering. And then there's the webinars. Webinars. This is our webinar, the first webinar. These are optional. You don't have to know. And they are also recorded. So don't worry if you can't make every week or every other. I'm doing every other week. So don't worry. You can always watch the recording. But if you come, you can always ask me a question. There's a Q&A section you can find in the in the more, if you press more on Zoom and then press Q&A, you can ask me a question. Okay, amazing. Then there's the follow along program, follow along Compost. Now for the follow along program, you do not have tutorials. No tutorials. You still have homework, but homework is not mandatory. Homework is optional. You just complete the assignments. If you want, you can complete them. And you have the webinars. They're also optional. So if you are not ready for a serious commitment, like the main Compost program, which we have 1,000 places, for the following program, we have infinite places. We are not limited. So yes, homework is optional, webinars is optional. You can complete, if you complete either program, you will get a certificate. So both programs, you will get a certificate. Which is, well, to be honest, is quite useless. Okay, certificate doesn't give you preference when doesn't get you places. The certificate itself does not count towards anything. It's just a great thing to have. As we are increasing in popularity, people know more about us, and they know that a Compost certificate is a serious thing, is a serious, yeah, okay. And I have to say a very important thing, like there are probably multiple ways a person could potentially cheat on, for example, to get on the program or to stay in the program. Yes, we require a regular submission of homework, especially with new technologies. One could potentially get ahead, get ahead, but that's not the point. Getting a certificate doesn't mean it doesn't do anything to you. As a matter of fact, if somebody was tried to cheat and then they got the certificate, and then they went to an Oxford interview and said, "I have a certificate," and they, "Whoa, wow, that's very cool. So you must know physics really well," and you will be probably asked much harder questions on your interview than if you didn't go to Compost. And if you don't manage to, if you have a Compost certificate and you can't answer some questions on physics, that will really play against you. So, okay, so Compost is for people who really want to study. The Compost certificate is a nice thing to have, but it doesn't give you anything. So yeah, that's what I'm trying to say. What else? Yes, how to get information about the program. So if you go to our website, there's the webinars, and so here you press here 12 webinars, and on the bottom there are recordings, and that's a place where I advise you to go. If you go to the recordings, so these are the last year's webinars on every topic. And I have done a webinar on mechanics, so you can see that number 19 is the same webinar that I'm doing today. Different problems, but the same thing. So if you are confused about the topic, you can always go back and watch last year or the year before, etc. You can click all Compost webinars, and that gives you access to all the webinars that has ever taken place, except maybe one or two when I forgot to press the record button. There's a timetable. So today's the, I don't know what happened here. It's the date is wrong, but it's obviously the, okay, I think it's the last year's timetable. I think it's a mistake. Yes, definitely a mistake. I will fix that, but yeah, apologies. Right, so I hope Complex analysis part of the assignment. We have complex numbers. There's an assignment on complex numbers. Yes, and that you will have that in year 13. Differential equation. Yes, you will have. So there's a question on complex analysis. You have complex numbers in year 13. Differential equations. Yes, you have differential equations, both partial and ODEs. You do ODEs in year 12 and you get partial in year 13. We don't go very deep into partial, but we do touch them. Can you take part in both Quantum Club and Compost? Yes, you can, but be aware of the time required, because you need to spend quite a few hours on Quantum, quite a few hours on Compost. So they're both highly intensive programs. Few people manage to do both. Yes, for people transferring some of year 11. Yeah, normally you would get a different tutor. Yes, we have year 11 tutors. We have tutors that specialize in year 12. Some tutors want to keep their group, and they might request to move to a different year group just to follow with their group. I'm not aware how this year this played out. Okay. Now, in physics problems, you are expected to use algebra. Okay. Putting the numbers in is usually the last step of solving a problem. So please be aware of that. So let's have a look at a typical problem where the use of algebra is highly beneficial. It's a very simple problem. A bag of sand is dropped from the roof of a 30-meter building. So you have a building and you have a bag of sand, and it falls. And when it hits the ground, it gets warmer because all the gravitational potential energy goes into thermal. Okay. You know that it's 30 meters tall, and the typical GCSE approach you person might take is say, well, I want to calculate the gravitational potential energy. Gravitational potential energy is mass times gravitational field strength times the height of the building. And that's where they get stuck, because they don't know mass. No mass. So you can't calculate gravitational potential energy. And some people get stuck here. Of course, a smart student would put a m instead of the mass and then try to figure it out. But yes, trying to put the numbers in times 10, gravity is 10, and height is 30, you get really stuck. So our advice, well, the way physics is done at university, the way physics is done at Compost, we do algebra rather than yes, we do algebra rather than arithmetic. So then you try to calculate the thermal energy, and thermal energy is mc delta T, where delta T is the change in temperature, C is the specific heat capacity of sand. For sand, the specific heat capacity is 800 joules per kilogram per degree Celsius. And once again, you get mass times 800 times T, which is delta T. So once again, you're kind of lost here, of course. Obviously, some of you can see the solution. How do we do things at Compost? We say, okay, gravitational potential energy is mgh. Cool, and we leave it like that. And then we say the thermal energy is mc delta T, the thermal energy transferred. And then we say, okay, assuming Assuming all GPE goes into thermal, then we can say that MGH is equal to MC delta T. Divide both sides of the equation by M, and magic M disappears. And then you divide both sides of the equation by C, and you get delta T is equal to G times H divided by C. So delta T equals GH divided by C, and that is your answer. Like, answer. And just as a cherry on top, we put in the numbers. So delta T is equal to G, which is 10 newtons per kilogram, multiplied by the height, which is 30 meters, divided by the specific heat capacity, 800 joules per kilogram per degree Celsius. Okay, so then 10 times 30 is 300. 300 divided by 800. 300 divided by 800, that's 0.375. Now the units, so kilograms cancel. Newton times meter is actually a joule. So Newton times meter and joule cancels. And you get 800 1 over Celsius. So Celsius goes on top, degree Celsius. And that is the answer. But this part is honestly an optional extra, right? It's a nice thing to have, but this is the important one, right? The algebraic answer. We will be for the solution, we will be looking for the algebraic expression. Of course, we do check the numerical values, but if you make a mistake in the calculation, you still get full marks. Okay, there are 7 questions. I'll look through. When do we get the assignment for quantum? I'm not sure. I think I don't do quantum club, so that's not my piece of cake. Not my thing. Do you do vector calculus in the vector assignments? Do you do vector calculus in the vector assignments? Probably not. Not really. At least, yeah, it's not much vector calculus. Can we do the assignment digitally on iPad with a digital pencil? It doesn't need to be done on paper. Digital pencil is perfectly fine. Yes, you can do it. How do tutorials work? How do tutorials work? You get assigned a tutor. Once you have a confirmed place at Compost, we ask you when are you available, and you tell us that you're available Monday, Tuesday, and Wednesday at 6, and we'll find a tutor which would be available at one of those times. Quite straightforward. You will receive emails explaining that thing. For year 13, are you able to do year 12 follow-up program and the year program in the same year? Yes, you can do follow along for 2 years if you want in 1 year. Yeah, that's a possibility. How many students will be accepted into the year 12 part of Compost? Well, we have 1,000 pupils overall, so I don't know the split. It will depend on the entrance tests. So this we haven't, the numbers are not finalized. Is dividing away and not getting rid of a solution? It's only getting rid of a solution if m could be 0, but m cannot be 0, therefore it's not losing a solution. Is there a sheet of the problems you're doing today? Okay, that's a very good question. If you go back to the webinars, there's the Year 12 webinar whiteboard. If you click on that link, that takes you to our whiteboard, which you can, and here's a link. So I'll put it in the chat. Actually, you know what? I don't need to put it in the chat because I can type the answer. And that's the whiteboard. I'll put it in the chat as well. It's the chat. Okay. Yes, thank you for asking that question because now you have the link. How do we submit the entrance assignment? You will have a Google form for submitting and you will receive instructions by email. It has to be submitted by the 5th of October, so somewhere in the next few weeks you will receive instructions. Is it one student per each tutor or a group of students for every one teacher? Is one student per each tutor? It's 8 students per tutor, and you have the same tutor for the whole year. Do we touch any work on the quantum mechanics at Compost? No, we don't do quantum mechanics. C is it's usually given. C is given. That's it will be given in the question. So it's not important because this is even a different topic. But yeah. How can you stand out to get accepted into Compos? You need to do really well on your entrance paper, on your first assignment. Okay. Yes, you need to do very well on your first assignment. How long does the Compos program last? Ends in July. Why would dividing by m remove a solution? It wouldn't. How long do you expect each assignment to take in the entrance test? I would imagine about 10-ish hours, maybe up to 10. 10 hours per assignment, maybe less. For questions on the problem sheet where we use logical, where we use logic, using writing. Yeah, just write. Write your solutions. Write solutions. As you would present. Well, it's hard to say. Yeah, just questions of the problem sheets where we use logic. Yeah, just write the steps. Write out the steps of your thinking. That's all you need to do. Okay. Can Compost help us get a scholarship? Can Compost help you get a scholarship? Well, in a way, yes, because if you do Compost, that means you do what 5 hours of physics a week, and that means you get really good at physics, and then you can get a scholarship. Yes, but some scholarships don't look at your academic achievements. Some scholarships look at your background. So in that way, no. So for example, if to qualify for a scholarship, you have to be from a certain region or a certain economical status. Yeah, we obviously we don't have any control over that, but you study and do well at Compos, of course, your academic achievement would be very high. You can get in. Yes. Can Compos help me get into Oxford? Same answer. Yes. 50% of our first cohort went into Oxbridge. So in a way, Compos helped them. But this is because they studied really hard. Not just because they did Compos, not because of the certificate. Are there a good resource to use for elements of the entrance paper we haven't been taught in school? You can use any resources. Hmm, Isaac Physics. You could use online lectures. I really like online lectures. I think I learned a lot. Walter Lewin is a person who does amazing lectures on physics. Very easy to follow, very easy to understand. Year 13 will, wow, there's a lot of questions. Year 13 will be able to submit and receive our certificate for our UCAS personal statement before the end of the year. I think we do letters. We do certificate. We do the certificates in July. But for year 13s, obviously we do the certificates somewhere in March. So if is March good enough for you, then the answer is yes. Compass benefit. Is there an example of a normal Compost assignment which we can see for a reference? Yeah, it's well, assignment 1 is a normal assignment. Yeah. Assignments look exactly the same as assignment 1. So you've seen the assignment. That's how typical assignments you get 10 of them throughout the year. Can Compost help the IMO? Yes, of course, but we're not math specialists. We're physics specialists. So we teach maths that is needed to be successful at physics. So there's some elements of pure maths which we don't cover. So it's not a full preparation for the IMO. How long after the live webinar will it be on YouTube? Typically within an hour or two. Sometimes it takes longer when I mess up something. When I mess something up, like yesterday, it took me about 6 hours. Is there? Okay. Is Compost's physics assignments useful for the design engineer? Absolutely. Yes. Absolutely. Yes. Wow, there's so many questions. Sorry, I have to stop somewhere because otherwise I've already spent half an hour and we haven't touched a mechanics problem. Some questions I've already got to prove problem solving for these questions, learning content scale the problems. Well, yeah, videos, good videos on the topic that can help you. Different literature. But yeah. Okay. I'll have to stop here. Sorry. I'll try to answer more questions later on. All right. So kinematics. Just a quick recap because we have done. If you open the assignment, where is it? If you open the assignment, webinars. Oh no, sorry, the assignments. If you open the assignment and physics year 12. For physics year 12, we expect you to know, to be familiar with assignments, year 10 assignments 3, 4, 5, and 6. So somebody was asking, does a typical assignment look like? So if you open these up, you will see 4 assignments for linear motion, motion in 2 dimensions, Newton's laws, and pulleys. Okay, so you're expected to know these things when you do our first assignment on mechanics. So please read through them or at least skim through them, especially if you're not very familiar. So kinematics. So a ball is thrown vertically upwards within. Yeah, we'll do some very simple questions today and some slightly harder questions, but yeah. Kinematics with one object. So a ball is thrown vertically upwards with initial velocity 20. How long does it take to reach maximum height? Well, we have initial velocity 20. meters per second. And the ball travels up, reaches the maximum height, and then falls down. To find the maximum height, well, we know the acceleration, because when the object is thrown upwards, it is in free fall, and the acceleration is 10 meters per second squared. Well, we can say it's negative because it's downwards. So we can say up is positive. So the y-axis is up is positive. And then we use something that we call the SUVAT equations, which you will, if you're not familiar with them, you will learn them in in this assignment. SUVAT equations. And they go as follows. S is the displacement. U is the initial velocity. V is the final velocity. A is acceleration. And T is time. And there are 4 SUVAT equations. Well, typically there's 4. Sometimes we can write 5. Final velocity is initial velocity plus acceleration times time. And the beautiful thing about this equation, it does not contain S. Second equation is displacement is initial velocity times time plus 1/2 at squared. This equation contains no v. 3. Displacement is u plus v divided by 2 multiplied by t. And this contains no acceleration. And I think this is my favorite equation because and this is if acceleration is constant. That's also important. Right. U plus v divided by 2. That means the average velocity is initial velocity plus final velocity divided by 2 times the time. That makes sense. This equation really makes sense. The displacement is the average velocity times time. 4. Final velocity squared is initial velocity squared plus 2as. And this equation contains no time. Right. So to answer this question, how long does it take to reach the maximum height? So we're looking for the time. So we write out SUVAT. We know that the initial velocity is 20. Acceleration is negative 10 meters per second squared. In A level, you use 9.8, but 10 is a good enough approximation. Now, when it reaches the maximum height, the speed is 0, the velocity is 0. So the final velocity is 0 meters a second. We're not interested in the distance, but we are interested in the time. So we use the equation that contains no s, and that is the first equation, v equals u plus at. We're looking for the time, so t is v minus u divided by a. So I'm rearranging, and then I substitute. So I always first rearrange and then substitute. Unless it is impossible. So v0 minus u, which is 20 meters a second, divided by acceleration, which is negative 10 meters per second squared, which makes it minus 20. Meters cancel, and you get second squared divided by 10 seconds, which is s cancels, and you get 2 seconds. That's A. B. The maximum height reached. Well, now we're looking for S, and we know that S is u plus v divided by 2 times t. That's a brilliant equation. U plus v, so that's 20 plus 0 divided by 2 times time, which is 2, which is 20 meters. And C, how long is the ball in the air before returning to the ground? Well, if it took 2 seconds to reach the highest point, it will take 2 seconds to fall back down. But I'm going to use a slightly different approach. I'm going to say, so for C, I'm going to say that the ball travels up into the air and it falls back down. So 20, and I'm going to write a suvat. So here the displacement, because it started and finished at the same point, you go up and then down, the displacement is 0 meters. Initial velocity is 20 meters a second. Final velocity is unknown, which we don't need. Acceleration is negative 10 meters per second squared. And time is a question mark. Time is what we're looking for. So we need the equation with no v, and that equation is s equals no v. S equals ut plus 1/2 at squared. Displacement is 0 equals u 20 times t. This is that rare case where you can't make t the subject because it's a quadratic equation in terms of t. Plus 1/2 multiplied by negative 10 multiplied by t squared. 0 equals 20t minus 5t squared. 5t squared minus 20t is 0. So here, one would say divide by t, which would make sense because t is not 0. But I'm going to factorize. So 5t, open bracket, t minus 4 is equal to 0. So either t is 0 or t is 4. And obviously, we need the latter. So t is 4 seconds. And you could also notice that at t equals 0, yes, the height is 0. The displacement is 0. That means you haven't moved you haven't moved at all. Okay, so that's the first problem. So we've answered all the questions. Maximum height is reached in 2 seconds. The maximum height is 20 meters, and it takes 4 seconds. Okay. Two cars from the same start from the same point at the same time. Car A travels east. So car A travels east at 20 meters per second, and car B travels north. So VB is 15 meters a second. How far are they after 10 seconds? Well, that's quite a simple question. So this car travels 200 meters, and this car travels 150 meters. How far they are apart? Well, they are. The distance is square root of 150 squared plus 200 squared, which is approximately. This is Pythagoras theorem. So 150 squared plus 200 squared, 250. Oh, I didn't expect. It's exactly 250 meters. All right, amazing. Okay, B. What is the relative velocity of B with respect to A? Well, here you can do it in two different ways. Well, in 10 seconds, they become 250 meters apart. So the relative speed is the relative distance divided by time. So it's 250 divided by 10, 25 meters per second. But also we can use the Galilean they call Galilean transformations, but also Galilean relativity. Basically, what does it mean? The relative velocity of B with respect to A. So you're sitting in the car A and you're traveling at, all right, let's just briefly talk about relative velocity. Relative velocity. If you're sitting in car A, you're traveling at 30 meters a second. There's a car B, which is traveling at 20 meters per second. And there's a car C, which is traveling at 10 meters per second. But these speeds are relative to the ground. So this is 30 relative to the ground, 20 minus 20 relative to the ground, plus 10 relative to the ground. Now, if your speed, so velocity, sorry, velocity of A relative to the ground, relative to the ground, relative to B, relative to A, relative to B, or relative to C. To ground, A, B, and C. Velocity of B, velocity of C. So the velocity of A relative to the ground is plus 30. The velocity of A relative to, velocity of B relative to the ground is minus 20. Velocity of C relative to the ground is plus 10. So plus is positive, left is negative. Cool. Now, relative to A. So basically, if you're sitting in car A, B is approaching you at 50 meters a second. So the velocity of B relative to A is minus 50 meters a second. So basically, you're sitting in car A, you can see car B approaching at 50. Because the direction is to the left, it's minus 50. But if you're sitting in car B and the car A is approaching you at plus 50, if you're sitting in car C, yes. If you're sitting in car A, the velocity of car A is 0 relative to you because you're not moving. You're sitting in the car and the car is stationary relative to you. So the steering wheel is in the same position where it was after 10 seconds. Yes, the car is moving, but you are inside the car. Velocity of A relative to C is plus 20. So if you're sitting in car C, you see the car A approaching you. And the velocity of B is, so the velocity of C relative to A, well, if you're sitting in car A, you see car C approaching you at a speed of 20, so minus 20. And the velocity of B relative to B is, of course, 0. The velocity of C relative to C is also 0. And then finally, we got the velocity of B relative to C. So you're sitting at C, you see the car B going backwards at 30 meters, so minus 30. And if you're sitting in car B, you see car C going to the right at 30, so plus 30 meters a second. So I hope that makes sense when we seek out relative velocity. So when we say a car is A is moving like that, and a car B is moving like that, and this is 20, and this is 15 meters per second, So if you're sitting in car C, oh sorry, car A, if you're sitting in car A, relative to you, the car B, so the car A is stationary. So you are sitting in car A. Car A is stationary in your frame of reference. of reference. It's not moving. That means car B is moving 15 meters per second north, and it is also moving 20 meters per second west. And that's incredibly important. So you're sitting in a car, you can imagine if you're driving past a tree, it looks like the tree is moving backwards, right? Obviously, you know your car is moving forwards, not the tree. But sometimes, especially if you're in a train, you don't know which train is moving. You can see out of the window that the other train is moving, and you can't tell which train, is it your train or the other train is moving. So just the way you're sitting in a car, you're driving past a tree, the tree's moving backwards. If you're in car A, it looks like the car B is moving backwards at 20 meters a second, but also 15 meters a second north. So the total velocity relative to A is like this, and this would be the square root of 15 squared plus 20 squared is actually 25 meters per second. And the angle is theta, and theta is arctan. So that's 15 over 20, arctan 15 over 20, which is 10, 15 over 20 is 37 degrees. Okay. So relative to B, relative to A, B is moving at 25 meters per second. So you're sitting in A and B. It looks like B is moving in that direction. 37 degrees, speed of 25 meters per second. So B 25 degrees, 37 degrees north of west. This is the way we give directions, 37 degrees north of west. Okay, so hopefully that makes sense. I'm rushing a bit because I'm realizing we're not on schedule. So problem 3, in the setting of problem 2, the cars pass the crossroads. Car A passes the crossroads at t equals 0 seconds. Right, so there's the crossroads. And car A passes the crossroads at t equals 0 seconds. And car B at 3 seconds. So car B is somewhere here, and it's traveling upwards. So what we want to write here is something that we call the equation of motion. Let's say that this is the x coordinate. This is the y-axis. Y-axis. And this is minus 3. Minus 3 seconds. So when t is 0, car A is here. But car B is 3 seconds away. So in the 45, minus 45 meters, minus 45 meters on the y-axis. So at t equals 0, car A is at the origin, is at the crossroads, and car B is at point 0 minus 45. That's the coordinate. Now every car A starts at 0, at x equals 0, and every second it travels 20 meters. So after t seconds, the position of car A is x equals 0, the initial position, plus the speed, 20 multiplied by t. And you can agree. So when t is 0, x is 0, right? You can check. When t is 0, x is 0. When t is 1, x is 20. And that makes perfect sense. Car A starts at 0. After 1 second, it is here. It is at 20 meters. After 2 seconds, it is at 40 meters, etc. Okay. I'm rushing a little bit, but if you're finding this confusing, please look at watch my previous webinars. Okay. Now car B starts at y equals negative 45 meters, and every second it travels 15 meters. After t seconds, position of B is y equals negative 45 plus 15t. Okay. What we have written down is called the equation of motion. An equation of motion gives the position of the object at any moment in time. Equation of motion gives the position of an object at any moment in time. And that's very important to understand. That's what an equation of motion is. And these are equations of motion because x gives you the position at any time t, and y gives you the position at any time t. Cool. So if the car A, so after some time, car A is here, and car B is here, the distance between the cars, so because this is x and this is y, the distance between the cars is x squared plus y squared square root. Right, so distance between the cars, distance between cars is d equals square root of x squared plus y squared, and that is square root of x is 20t squared plus negative 45 plus 15t squared. Now, we need the minimum distance. So we can square it, square both sides. So d squared is 400t squared plus 15, so 225t squared minus 90 times 15, 1350 t plus 45 squared, 2025. What we're going to do next is when we're going to complete the square. So 400 is 625 t squared minus 1350 t plus 2025. So d squared is 625 open bracket t squared minus 1350 divided by 625 minus 2.16 t plus 2025 divided by 625. Well, I don't need to do that, plus 2020. So completing the square, 625 t squared minus 2.16 t plus 1.08 squared is 11664 minus 625 times 1.1664 plus 2025. And I can see that this is d squared is equal to 625, open bracket, t minus 1.08 squared plus 2025 minus 65 times 1.1664, 1296. Cool. So d squared is minimum when t is 1.08 seconds, because you can see that this expression is minimized, has a minimum value when t equals 1.08, and d squared minimum is, well, so you substitute is 1296, so the minimum distance is the square root of 1296, which I'd be very surprised if it's wow, it's 36 meters. So the shortest distance between the two cars is 36 meters, and this occurs where after 1.08 seconds, so car A has traveled about here, car B has traveled about here. Okay. Minimum distance. Cars. So the question, what the question was, what is the closest distance between the cars? The answer is 36 meters. And at what time do the other cars the closest? They're the closest when t equals 1.08 seconds. All right. We have a question like that in the year 10 assignment, so you can have a look at that. Right. A 5 kilogram block is pulled along a horizontal surface by a constant force of 30 newtons. The coefficient of kinetic friction between the block and the surface is 0.2. We call it dynamic friction. Dynamic. Draw a free body diagram. Okay, so 5 kilogram block, horizontal force of 30 newtons. The coefficient of friction, so mu, is 0.2. And okay, so there's a surface. So we need the forces acting on the block. So that's 30 newtons. There's the mg force. There's the normal reaction force from the bottom. I'm drawing it at this lower surface because that's where the normal reaction acts. It acts at the lower surface. So that's the normal reaction. And then there's the friction. And the friction, because it is sliding, the friction is equal to mu times the normal reaction. And the object is accelerating that way, acceleration. So Newton's second law says that mass times acceleration is the sum of forces acting. And because we know that the normal reaction is the same as mg, we can write it, it's the total horizontal force, so mass times acceleration, is the force going forward, so it's 30 newtons, minus, you know what? I'm just going to label this force F. F minus mu n. And I'm looking for acceleration force. So I've done A, now B. Acceleration is F minus mu n divided by m. Now, normal reaction has to equal to mg. Normal reaction has to equal to mg because the vertical forces are balanced. It's not moving up or down. So I can plug that into here. So it's F minus mu mg divided by the mass of the block, and that's your acceleration. You can finally put that in. So that's 30 minus mu, which is 0.2, times 5, times g, which is 10, divided by the mass, which is 5 kilograms, and we get, what do we get? 20 divided by 4 meters per second squared. Sorry, I did not use the unit, but we do expect you to, right? Newtons, 5 kilograms, meters per second squared, 5 kilograms. So kilograms cancel, and you get meters per second squared. Okay, cool. All right, so that's for the problem on dynamics. Problem 5. Two masses, 1 kilogram and 6 kilograms, are connected by a light and extensible string over a smooth pulley. Okay, so here we have a pulley which is attached at the ceiling, and we have two masses, M1 and M2. We need to find the acceleration of the system. Well, we can see that M2 is heavier than M1. That means that this block is going to accelerate downwards. And this block is going to accelerate upwards. So we draw the first block separately. We draw the block M1. The tension is up, so the rope is pulling the block upwards. That's one of the objects the block is interacting with. The other force is downwards, and that's M1G. That's the force pulling down. That's the gravitational force pulling the block down. The block is accelerating upwards. And this acceleration, the acceleration is caused by a force, right? That's what Newton's second law says. Mass acceleration is equal to the sum of forces. So the total force. So mass m1 times the acceleration of the block is equal to the forces going up minus the forces going down. So T minus m1g. And that's our first equation. Now we draw the second block. Draw the second block, M2, and it's accelerating downwards. And why is it accelerating? Because it's being pulled down by M2G, and is being pulled up by the force of tension. And of course, M2G is greater than the tension, and that's why it's falling down. So we write MA equals the sum of forces, or M2A, mass times the acceleration of the block, equals the sum of forces. So forces going down, so M2G minus the tension in the rope. Now the tension in the rope is the same because the rope is light and there's no friction in the pulley. So we have these two equations. We can add the two equations. So equation 1 plus equation 2. And we get M1A plus M2A on the left side. And on the right, T cancels, and we get M2G minus M1G. A, M1 plus M2, open bracket, G, M2 minus M1. So the acceleration of the system is M2 minus M1 divided by M1 plus M2 times the gravitational field. And that's the acceleration of the system. Amazing. So now we can work it out because we know the values. Acceleration is m2 6 minus 4 divided by 6 plus 4 multiplied by 10 meters per second squared. This is obviously kilograms and kilograms and kilograms and kilograms. Kilograms cancel out. And you are left with 6 minus 4, that's 2. 2 divided by 10, so 0.2 times 10, which is 2 meters per second squared. So that's the acceleration of the system. And now the tension in the rope, you can take any of the equations. So that is tension is M1A plus M1G. And that is, does that really make sense? Of course, yes, it makes perfect sense. So it's M1A plus G, and that is 4 kilograms multiplied by 2 plus 10, which is 48 newtons. Cool. So that's how we do this. We have a very similar question in the assignment where there's also an example of this. So I'm rushing a bit, so don't 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 worry if you're not managing to follow. You can always rewatch the video later. A block of mass 5 kilograms rests on a rough horizontal table. So 5 kilograms. It is connected by a light string over a pulley at the edge. So there's a pulley, there's a rope, and if you're having a block of mass M2. So M2 is 3 kilograms, and this is M1. Now we need, obviously this block is accelerating to the right, and this is accelerating downwards. So we need the forces on each block. So we'll start with the easy one, the M2. We draw the M2. We always draw the single object and the force is acting on that object. So there's the gravitational force pulling down, M2G, and there's a tension in the rope, tension pulling up. And we can write, and because it is accelerating downwards, we can write that mass acceleration is the sum of forces. Or in other words, forces pushing you forward minus forces pulling you backwards. Mass times acceleration is the total force. This is Newton's second law, and it's really important to get it, to understand it. Mass times acceleration for a single object is the total force. Or in other words, the forces pushing you forwards minus the forces pushing you backwards. So m2 times the acceleration is the force pulling you forwards, that is m2g, minus the force pulling you backwards, which is t, and that's your first equation. Now you draw the second block, or the first block, m1. Now for m1, there's a tension in string, tension pulling you forwards. There's the friction pulling you backwards. There's the normal reaction force pushing up, and there's the gravitational force pulling down. So this is M1G. This is the normal reaction force. And this is the friction force. And we know that the friction force is mu times N. So for vertical forces, we know that N minus M1G must equal to 0 because the total force is 0. So in other words, N equals M1G. And horizontal, we have mass acceleration is equal to the sum of forces. So m1 times a, it's accelerating to the right, is equal to tension minus mu n. But we already know that n is m1g, so it's t minus mu m1g. Amazing. So that's your second equation. And what do we want? We want to know the acceleration of the system and the tension. Acceleration and the tension once again. Right, so we add the two equations. Equation 1, equation 2, equation 1 plus equation 2. And we get m1a plus m2a equals m2g minus t plus t minus mu m1g. So t cancels. Acceleration m1 plus m2 equals m2 minus mu m1 g. So acceleration is m2 minus mu m1 plus m2 g. And okay, that is normally how you would write the answer. So let's put in the numbers. So m2 is, what is m2? M2 is 3 kilograms. 3 minus 0.25 times m1, which is 5, divided by 3 plus 5 times 10. I guess so 3 minus 1.25 divided by 8 times 10, 2.1875 meters per second squared. Of course, we don't leave it, which is approximately 2.19 meters per second squared. Amazing. And then determine the acceleration of the system and the tension. Oh, the tension, we can use any equation to find the tension. I think we'll use the first equation. So in the first equation, we have T equals M2G minus M2A. And that is M2G minus A, which is M2 is 3, I believe. 3 kilograms, yes. Oh. 3 times 10 minus 2.19, which is approximately 3 times 10 minus 2.19, 23.4 newtons. Right, there's a question. Yes, kinetic friction is when the object is sliding. We also call it the friction of sliding. Okay, the monkey and the hunter problem. A very interesting one. A hunter aims a tranquilizer dart gun directly at a monkey hanging from a branch. At the instant the hunter fires, the monkey let go of the branch and begins to fall freely under gravity. Assume that the dart leaves the gun with speed v and air resistance is negligible. Show that the dart will always hit the monkey regardless of the dart's initial speed, provided the monkey is in range. Oh, fascinating. So, well, let's see what we can do. Let's introduce a system of coordinates x and y. Let's make some assumptions. Let's say the hunter is a very tall hunter, so 2 meters. 2 meters tall. And they're shooting a gun at 20 meters a second. Is it 20? Oh, V. Well, okay. Shooting a gun at, yeah, 20 meters a second. Actually, you know what? Let's make it 50 meters a second. Assume that the monkey is initially 100 meters away. And it is at a height of 40 meters. 40 meters, so that's 40 meters. Okay. So for the monkey, I'm going to use vectors for this one. And Suvat. The initial, no, I'm going to use, instead of Suvat, I'm going to use this equation. The position of the monkey, R is the radius vector of the monkey, is the initial position of the monkey, plus the initial velocity of the monkey times time, plus 1/2 at squared. You could recognize this as one of the Suvat equations, but now it is a vector. We know that the initial position of the monkey is 140. So R is of the monkey is 140. That's the initial coordinates of the monkey. Plus the initial velocity of the monkey, which is 0, 0, times time, plus the acceleration of the monkey is 0 minus 10 because that's the gravitational, that's acceleration of free fall. So horizontally it's not accelerating, vertically it's accelerating at minus 10. So it's 1/2 multiplied by 0 minus 10 multiplied by t squared. So let's simplify this. The position of the monkey, the radius vector of the monkey is 100 plus 0, well, 100, and 40 minus 5t squared. Oh, lovely. So that's the initial, that's the position of the monkey at any moment in time. So that's the equation of motion. Equation of motion of monkey. Okay. And you can see that the x coordinate, so what is the position, right? So the radius vector is literally the x position and the y position of the monkey. And you can see that the x position is always 100. Yes, the monkey always has x coordinate 100. Okay. Now the dot. The dot. The dot also has the same equation of motion. RD is R0 plus UT plus 1/2 AT squared. And acceleration is also 0 minus 10. It's in free fall. The dot, when you throw something into the air, it's in free fall. And we are going to write RD is equal to R0. It's the initial coordinate, so it is 0, 2 plus the initial velocity multiplied by time plus 0 minus 10 times 1/2 multiplied by t squared. Now we need to find the initial velocity. Well, we can initial velocity horizontally and vertically. So the initial velocity horizontally, this is the angle theta. So the initial horizontal velocity is 50 times cos theta. And the initial vertical velocity is 50 sine theta. And what is theta? Well, if this is 100 and this is 38, so theta is arctan of 38 divided by 100. So arctan 38 divided by 100, it's 20.8 degrees. 20.8 degrees, because that's remember the hunter is directing the gun at the monkey. The dot gun, of course, 20.8 degrees. So we can calculate the initial velocity. So 50 times cos of the answer, and that's 46.7 meters per second. And the vertical velocity is 50 times sine 20.8, 17.8 meters per second. All right, so we can put that in. So the position of the dot is 0 plus 46.7 t plus 0 t squared, 2 plus 17.8 t minus 5t squared. And that simplifies to 46.7 t. And this is 2 plus 17.8 t minus 5t squared. All right. And we need to prove that the dot hits the monkey. How do we going to do that? Well, I I suppose we can do something like this. Let's go on to Desmos. And try to draw point. So the first is the monkey. It's M. Its coordinates 100 and 40 minus 5t squared. Zero to 5 seconds. Let's see if that gives us something. Oh, okay, that's the path of the monkey. 40 minus, add slider A. Okay, lovely. So that, yes, that's how the monkey moves. 5 g squared. No, I don't want A. Okay. Time is A. Okay. And I'm going to change that A from 0 to 5. And the step is 0.1. And let's see. Lovely. So what I have a monkey. Okay, repeat in one direction. That's what I want. So I have a monkey that is starting at 40. And 0 to 5. Okay. So yes. So a monkey starts at 40 and falls down. Okay, then it tries again. Okay, cool. And now let's draw the dot. And this is 46.7 times A. And then 2 plus 17.8 A minus 5A squared. Pause. It took about, what, 2 seconds to hit. So we need to change that from 0 to 2.5. Step 0.05. Okay, so now you can see. You can see what we've done. Can we actually draw these? Yeah, we can, certainly. T 1 to 2.5. we can do this. T. T 2.5. Right. So the dart starts at 2 meters initial position, and then they meet up here. So let's see if I can. Okay. Can we do it slower? You can see. Yes. Very satisfying. So you go. The monkey starts to fall, falling, and then they hit. They hit each other. Now, if I were to change the initial speed of the if I were to change the initial speed of the dart, let's say I double the speed, or more like half the speed. Let's make, I'm halving the initial speed, so 46.7, that's will be 23.35, and instead of 17.8 divided by 2, that's 8.87. 8.87. So I'm making the dart twice slower. I need to increase the time because it will take more time to hit the monkey. So let's take it 5, 5, here, 5, and of course 23.35 and 8.88. Okay, let's see what happens now. Play. Boom. You see? Very satisfying. Can I share this? I think I can. Don't think I can share it directly. No, unfortunately. Right. Of course, yes, the monkey would be below the ground, but assuming that, I don't know, there's a cliff. We never know. You know, these monkeys and hunters. But yeah, if you even if you change the angle, it would still be the same. And I don't know, I I find those things are really there's some really nice videos. If you Google quantum boffin, monkey and hunter, it is an amazing video where you can actually see the experiment in real life, not with a real monkey, of course. Right. Cool. I think I'll finish here because I really don't have time to do the next problem. I don't want to close that. Yeah. Very satisfying. Okay, so I hope that was useful in some way for you. Um, please use everything or watch my videos. Watch the previous webinars. Read through assignment 10, assignment of year 10, if you're confused. Okay, so what do we have here? Not a question, but a good luck to everyone getting results tomorrow. Yes, of course. Definitely good luck. Desmos, can you use Desmos for a solution? As part of your solution, yes. I don't see a problem with it. Okay. If you want to explain your solution using a Desmos, why not? If the mass of the monkey was light or heavy, would that affect the monkey got hit? No, it wouldn't. Of course, if the monkey was very light, it would like fall down like a leaf, right? Because of the air resistance. But assuming there's no air resistance, so for any reasonably heavy monkey, that would work. Of course, unless you're firing from 3 kilometers away. But if you're firing 3 kilometers away, there's all sorts of other issues, including why would you do that? Okay. Can we find the minimum speed needed for the dart to hit the monkey above ground? Oh, that would be a very good question. Yes, but it's not a very. It's a good question, but not a very difficult one. It's just you want to make sure that the bullet doesn't hit the ground before reaching the horizontal distance of the monkey. Because if the monkey is 100 meters away, you need to make sure that the bullet can travel 100 meters. Because if the bullet and the monkey meet underground, that simply means that the bullet cannot fly 100 meters without crashing into the ground. So yeah. For these kinds of questions, do we have include statements that the equation is valid at a certain range? Not. It's up to you. It's up to you. Honestly, there's it's a too much technical detail. If you get the correct equation, we won't punish you. We won't penalize you for not having the correct ranges in place. We're not petty. Okay. Does the proof demonstrated work for any values? Well, it's up to you to find out. You can play around with the parameters. I chose this method. Could use a different method. For any problem we have, there are multiple ways you can solve it. Okay, there's no single correct way of doing it. If the monkey didn't fall in a straight line, would this affect whether the monkey was hit? Why would the monkey not fall in a straight line? I mean, the idea is that the monkey holds the branch and then lets go. It will fall vertically downwards, unless there's some kind of gravitational anomaly, or it is on board the Hail Mary ship. If you haven't read the book, do recommend it. It's quite a lot of compost material in that book. Is there a certain rule of projectile motion that makes sure that the monkey is always hit? Well, in a way, yes. You have the independence of the horizontal and vertical motion, and you could actually use Einstein's principle here, Einstein's equivalence principle. You could actually argue that once the monkey lets go, the monkey doesn't move. So Einstein would say the monkey is stationary. Einstein would say the monkey is stationary and the bullet is traveling in a straight line. That's what he would say. And it's the gravitational field of the planet that is curving space-time in such a way that makes the bullet travel in a curved path. That's really, really exciting, but it's not way out of the topic. I have to finish. Sorry, could you please drop the book name? Project Hail Mary by Andy Weir. Project Hail Mary. Okay. Yes. Yes, the book is Project Hail Mary. Algebraic altering the velocity. Yes, you can certainly prove it algebraically. Yes, and you should if you want to do this question. Okay. All right. So I hope you enjoyed today. Nice to see everyone. And yeah, good luck with your results, of course. And see you in 2 weeks' time for some maths. Right. And thank you, Angela, for helping today and answering some of the questions.